Welcome back to Unit 14. This is Part 2. We will be looking at entropy as a quantitative value today, doing some calculations using a formula that you will find on your reference sheet. And we will define Gibbs free energy, talk about its importance in determining spontaneity, and also work with it quantitatively. The third law of thermodynamics states that the entropy of a pure crystal at 0 Kelvin is 0. This gives us a starting point. What this is basically saying is at 0 Kelvin, which is also known as absolute zero, all particles in a substance cease to move, which means they have perfect order. Any substance that is at a temperature higher than 0 Kelvin would have some sort of disorder. So all substances have an entropy value, and those entropy values will be greater than 0. You can find those entropy values in your book, in the back appendix. You'll find them within the problems that we will be doing, and you can also use your yellow reference sheet that I gave you at the beginning of the year. The equation at the bottom of the page can be found on your reference sheet, and it states that the entropy of a reaction is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. In example 6, we need to find the standard entropy change for the synthesis of carbon dioxide. So we will start by looking at the products, and notice that we have 2 moles of CO2. So to start this reaction, we will take 2 times the entropy of CO2, which is 213.6 joules per moles Kelvin. And then we will subtract it from the entropy of the reactants. There are 2 reactants this time, so we're going to do 2 times 197.9 plus oxygen, which is 205.0. When we add all of these up, we end up getting negative 173.6 joules per moles Kelvin. This unit is very important. I want to mention at this point that it is in joules, unlike enthalpy, which is usually given to you in kilojoules, and Gibbs free energy, which we'll see in a little bit, which is also given to you in kilojoules. So when we work with entropy values later on down the line, we'll have to be very careful about converting this value into kilojoules to do other calculations. I also want to mention that we could have predicted that the entropy would decrease here because we're going from 3 moles of gas to 2 moles of gas. So qualitatively, we would have said there was a decrease in entropy, and when we solved it out quantitatively, you can see that we got that negative sign, which thus tells us that entropy is decreasing in this reaction. Example 7 is going to be done the same way as example 6. We are going to start by looking at the products, and in this case right here we have 2 moles of SO2, which is 248 joules per moles Kelvin, plus 2 moles of nickel oxide, which is 38 joules per moles Kelvin, and we're going to then subtract the sum of the entropy of the reactants, which will be 2 times 53 plus 3 times 205. When we solve this out with a calculator, we end up getting negative 148 joules per mole Kelvin. Qualitatively again, we can notice that we are going from 3 moles of gas to 2 moles of gas. That is a decrease in entropy, and that negative sign once again is proving that entropy will decrease in small amounts in this reaction. So Gibbs free energy is another thermodynamic function that we will use to predict spontaneity. It is a state function, just like entropy and enthalpy. However, it can't be measured directly, so it has to be calculated from other measurements. We're going to define it as the amount of energy available to do work at a given temperature and pressure. This value is never really achieved because some of the free energy is changed to heat during the reaction, so it can be used as work. So at this point, I just want to stop and remind you, in the first part, we talked about the entropy of the universe being able to predict the spontaneity of a reaction, but it was hard to measure. So I mentioned there would be another thermodynamic function that would be able to do that for us. And we're at that point right now. Gibbs free energy is going to be the way that we predict if a reaction is spontaneous or not. Please understand that the two last calculations that we did were calculating the entropy of the reaction, not the entropy of the universe. So understand that we will use that in a future calculation, but Gibbs free energy is what we're going to use to determine if a reaction is spontaneous or not. So this reaction is what I call the mama of the thermodynamic section. Basically, it says the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. Notice that all of the thermodynamic functions are taken at their standard conditions. When we calculate delta G using this equation, we will be able to predict the spontaneity of a reaction at constant temperature and pressure. This equation is also on your reference sheet. When we calculate delta G and it comes out to be a negative number, we will determine that the reaction is spontaneous as long as the temperature and the pressure is held constant. If the delta G is positive, it will be non-spontaneous in the forward direction, but spontaneous in the reverse. And if delta G is 0 at constant temperature and pressure, the process is at equilibrium. This is an important chart because it's going to give you the 4 possible scenarios that you will run across when determining if a reaction is spontaneous or not. If you recall from part 1, we said that a reaction would always be considered spontaneous if it was an exothermic reaction with a negative delta H, and it would increase in entropy. So that would be a positive delta S. So if we were to do this scenario where we put in the negative sign here minus a positive, and we did some math, you would see that the delta G would always be negative. And of course, the reaction would be considered spontaneous, and it doesn't matter about the temperature. The complete opposite of that scenario would be a decrease in entropy and an endothermic reaction, a delta H that is positive. So this would be not spontaneous in the forward direction. It would be spontaneous in the reverse direction. If we were to put in the signs, positive, minus, and negative, mathematically it would show us that delta G is positive, and a positive delta G tells us that the reaction is non-spontaneous, and it doesn't matter what temperature you're at. The other 2 scenarios are temperature dependent. If we have a scenario where the enthalpy is positive and the entropy is also positive, you will see that the T delta S factor is very important in determining whether the reaction will be spontaneous or not. If this value is very large due to a high temperature, then we would find out that delta G would be negative. However, if the temperature was very low, then the enthalpy factor would be important, and we would find that the delta G would be positive. So we say at high temperatures in this scenario that the reaction is entropy driven, because the T delta S factor is what is going to make the delta G negative. And lastly, if we have a negative delta H and a negative delta S, once again, we would find out that one of these factors is going to create spontaneity. If our delta H was very high and our T delta S was very low, then the reaction would be spontaneous. Delta G would be negative. So we say if the temperature is really low, then the delta H would control delta G being negative. We would then say the reaction is enthalpy driven. So in this first scenario, the reaction is both enthalpy and entropy driven. In the last scenario, it is not spontaneous, so it's not driven by anything. But the two middle scenarios, when you have a positive delta S and a positive delta H, we say the reaction is entropy driven if temperature is high, and it's enthalpy driven if you have a low temperature. So just to make sure you understand the importance of this equation, you will be given scenarios where you will have to determine if the reaction is spontaneous or not by looking at the value of delta G. Is it positive or negative? If we take a look at the bottom right corner, you will see that there is a exothermic reaction. So the delta H is negative and the entropy is increasing. Remember, we said that these two scenarios always create a spontaneous reaction. It doesn't matter what temperature you're at, the reaction will always proceed in the forward direction without outside intervention. The complete opposite of that would be an endothermic reaction, a positive delta H, and a decrease in entropy. And that will tell us that the reaction will never be spontaneous in the forward direction. So we're going to say non-spontaneous. And I also want to mention at this time that the College Board does prefer that you use the words thermodynamically favorable when you are referring to a situation that is spontaneous. In the upper right-hand corner, we have a positive minus a positive. So if we are at high temperatures, the reaction will give us a negative delta G, and the reaction would be considered spontaneous. To determine what temperature that would have to be, you can do the following. Delta G would become 0 because we would be in a state of equilibrium, and then we would do equals 18,000 joules minus T times 60 joules. When you solve for temperature, it would end up being 300 Kelvin. So any temperature above 300 would be spontaneous. And then in the left top corner, if we had a negative delta H minus a negative entropy, in order for our reaction to be spontaneous, we would have to have low temperatures here because we want the delta H to control that. And of course, we already figured out what the temperature would be, so any temperature less than 300 Kelvin would be would give us the ability to see a spontaneous reaction. There are other ways to measure delta G for a reaction. We just looked at the MAMA equation, but we could also use Hess's law like we did with enthalpy reactions in Unit 13, as well as modified Hess's law, which is very similar to what we did with enthalpy as well in Unit 13. If you were to use modified Hess's law, we would use an equation very similar to what we did when we were calculating the heat of a reaction. To calculate the free energy of a reaction, you would just simply subtract the free energy of the reactants from the free energy of the products. You can get the values for free energy in the appendix or in tables that I will provide to you. One thing I do want to mention is that the standard free energy of formation for any element in its standard state is 0, just like we talked about in enthalpy. The only time that would not be the case is if we were looking at entropy. Example 8 asks us to calculate the standard free energy change for the following reaction. It is a combustion reaction. We will do this very similarly to our entropy calculations in the earlier part of this presentation. So we'll start off with our products. We have 12 moles of CO2. The free energy of formation is negative 394.4 kilojoules. We're going to add that to 6 times negative 237.2 kilojoules. I want you to be aware that this was liquid water. If it had been gaseous water, the Gibbs free energy of formation would have been different, and that also would apply to the enthalpy and entropy values. So we have to be very careful about the physical states of our substances, especially if they give you multiple substances in a table that are very similar but just different in state. So then we're going to subtract the free energy of formation of the reactants. We have 2 moles of benzene here, so 2 times 124.5. And then, of course, we have oxygen, but oxygen is an element in its standard state, so the Gibbs free energy value is going to be 0. It doesn't matter that there are 15 moles of it. And when we put that into the calculator, we end up getting a value of negative 6,165 kilojoules. And that negative sign is going to tell us that the reaction is spontaneous. That is the most important thing in this calculation, is figuring out if the reaction is thermodynamically favorable, which once again, College Board prefers those words over spontaneous. We could use just plain old Hess's law to also calculate the delta G. Remember, in Hess's law, we are manipulating equations to get the net reaction. So I want diamond solid on the left, and I want graphite solid on the right, which means I am going to flip this equation. So I'm going to get CO2 gas yields C graphite plus O2 gas. When I flipped the equation, that made me flip my sign, and then we can see that the CO2s will cancel out, the O2s will cancel out, and we'll be left with C diamond yields C graphite, which means now all I have to do is add these equations up, and that will give me negative 3 kilojoules. Yikes. And thus the reaction is slightly spontaneous. At equilibrium, the free energy of a reaction is actually equal to 0. A few slides back, I showed you how to plug in 0 into the delta G portion of the Mama equation, and to use the delta H and the delta S values to calculate the temperature. Remember, that temperature was kind of like the fulcrum. It was the teetering point as to whether a reaction would be spontaneous or non-spontaneous. When we're looking at physical changes, this equation becomes very helpful because it will tell us at what point a substance will be going through a phase change, whether it would be going through melting and freezing, equilibria, or vaporization or condensation equilibria. So this equation, the Mama equation, which you see right here, will allow us to calculate the temperature of boiling point, freezing point, melting point, or condensation point during a phase change, as long as we remember that when we're at a phase change, we are in equilibrium and delta G is equal to 0. Example 10 shows us how this is done. So if we write the Mama equation down, delta G is equal to delta H minus T delta S, and we substitute in the values. Remember, this is a phase change. Liquid bromine is converting to gaseous bromine, so delta G would be 0. Our delta H is going to be 31 kilojoules per mole. I'm just going to actually change that to 31,000 joules per mole. And then I'm going to subtract the temperature and the entropy value of 93 joules per mole Kelvin. So when I take 31,000 and I divide that by 93, I will get a temperature of 333 Kelvin at equilibrium. So then we can go ahead and we can plug that value back into this equation right here. And if we picked a number like 400, using our delta S and our delta H, we could calculate the value of delta G, and then that could also tell us if the reaction would be spontaneous or non-spontaneous at that higher temperature, or if we chose a lower temperature, it would tell us if it was spontaneous at the lower temperature. So if you did plug 400 in here, we would realize that temperatures greater than 333 Kelvin are spontaneous, and temperatures less than 333 Kelvin would be non-spontaneous. I also want to mention that we could have left our joules, we could have left the delta H in kilojoules, and we could have changed the entropy value to kilojoules. So we could have also done 31 divided by 0.093. It's whatever your preference is, you would still get the same answer of 333 Kelvin.